Okay, guys, we're going to look at 12.4 and 12.5. We're going to have a quick overview of this. This is general, or 12.4 is general, okay, general curvilinear motion. Okay, so in the previous chapters, we were looking at straight line motion, but now we look at a particle that moves in a curve, okay? And there are a few different ways to analyze curvilinear motion, and the different ways are based on different coordinate systems, okay? Coordinate systems. So here we've got the same particle moving, you know, at one point it's there, at another point it's there, it's moving in a curve, not a straight line. And there's a few chapters here, specifically chapters 12.5, 12.7, 12.8, that give us different coordinate systems on how to analyze this, okay? So we'll see in a minute. 12.5 gives us a specific coordinate system. So I don't know why this is not zooming, not focusing. Okay. So sorry about that. I hope you guys can still see this because it doesn't look very clear on my screen. Let's try to bring this a bit closer. Okay, but anyways, the point is, guys, that these three chapters give us different coordinate systems for analyzing curvilinear motion. So 12.5, which we'll touch now, is rectangular coordinate system. That means we look in the X, Y, Z direction. Okay, it's just a quick way of saying that. 12.7, we're looking at normal and tangential components. And 12.8, which we don't do in this course, is cylindrical components. Okay, the point that I'm trying to make is we've got this motion, curvilinear motion, but but we analyze the problem using different coordinate systems. Okay, so that's just a quick overview of that. General curvilinear motion, we define the position of the particle using a position vector. R is our position vector, okay? But what you notice is we don't really say what that looks like yet. All we're saying is that the instantaneous position of the particle as it moves on this curve is defined by a position vector, okay? Then if this particle moves to another position, then I don't want to go into all the details, but this change in position is given by delta R. So delta R is your change in position, okay? And that is your displacement. So we have our initial position, our final position, and our change in position is our displacement, our delta R. In straight line motion, this was delta S, but now in curvilinear motion, it's delta R. And as we make this shorter and shorter time span between the two different position vectors, we will see that this delta R would end up becoming tangent to this curve, okay? So that leads me into the next thing. Our velocity, even our average velocity, is given by delta R over delta T. That is our displacement over time, okay? And our instantaneous velocity is given by dr dt. And what we see, as I said right now, as the time between these two different position vectors becomes smaller and smaller, we will see that the direction of this vector, delta R, this vector here, becomes tangent, okay, tangent to the curve. And so that also shows us that our velocity vector, okay, if there's our curve, at that point, our velocity vector will be tangent to the curve. Okay? So this is all just basic stuff here. Let's move on to our acceleration. Our average acceleration is given by delta V, delta T. Okay? Our instantaneous acceleration is dV, dt. Okay? So you can go to, I think it's page 33, and you can go and look at the derivation. But the velocity vector is always tangent to the path. At any point, it's going to be tangent. At any point, it's tangent. The velocity vectors are always going to be tangent. And if there's my path, the acceleration vector will always be somewhere on the inside of the curve. There's the path. My velocity vector will always be somewhere on the inside. So many of you have come to me over the last few days and said, is it always perpendicular to the velocity, or can it be outside the curve? So number one, it can never be outside the curve. Because why is the particle moving in this kind of curvilinear fashion? It is exactly because there is an acceleration towards the inside. Because there is a force being applied to this particle, which is causing it to accelerate in that direction. That is why there's a curve in that direction. So you can't have a net acceleration over in that direction, but it's curving in this direction. A net acceleration. Okay? And there are specific cases where the acceleration is perpendicular to that curve. Okay? But those are specific cases. But in general, the acceleration vector is always pointing to the inside of the curve, the inside. And the velocity vector is always tangent to the curve. Okay? All right. Now, in 12.4, all we defined was R, V, and A. General, in a general sense. And what I said was, in 12.5, 12.7, and 12.8, we are describing and analyzing a curved motion using different coordinate systems. The first coordinate system we're going to look at in 12.5 are rectangular components. Rectangular components. This just simply means, remember our Cartesian coordinates in first semester? X, Y, and Z axes. X, Y, Z coordinates, okay? So, here they are. X, Y, Z, and there's the particle. Remember in 12.4, all we said was, there's my position vector, but we never said what it looks like. Now, this is what it looks like. There's my position vector, but it's given by xi plus yj plus zk. So the position vector, how far in the x, how far in the y, and how far in the z do I go, right? To get from that position to that position. So a position vector is what is the position of the particle relative to some other reference frame, okay? So please go and recap what is a position vector. But the point I'm trying to make is in 12.5, we are looking at rectangular components. That is the coordinate system we're using to describe the motion of the curvilinear motion of the particle. So if our position vector looks like this, I'm not going to go into the whole derivation right now, meters. Our velocity vector is x dot I plus, because v is dr dt, so v is x dot I plus y dot j plus z dot k meters per second. And what is x dot? It is just dx dt. It is vx. What is y dot? It's dy dt, vy, etc. Okay? That's all that is. So this is vxi Vyj, Vzk. What is our acceleration? Again, dv dt gives us Vx dot I, Vy dot j, Vz dot k, meters per second squared, which is then AXI, AYJ, AZK, meters per second squared. Okay, so that's the basic idea. We're looking at a specific coordinate system here, and that is the rectangular components. This is how we define the position of a particle, and we use the same type of coordinate system when dealing with our position, our velocity, and our acceleration. Okay, in the next couple of videos, we'll do some problems. Cheers.